Hello, everybody. In this video, I will go through the concept of orthogonal complement of a vector space, and we will do a couple of examples for the orthogonal complements of a vector space, of a subspace. Uh, Now, I would like to give a first definition. This is for the course Maths 2501 and 2099 on the concept of linear algebra at the University of New South Wales, related with the week 4, week 5 work. W is a subspace. Assume that we have a subspace W, which is given to us. And now we would like to find out the complement. In order to be able to talking about the orthogonal complement, we need to have a dot product definition. As you realize it by now from your lecture, is that dot product in a general form is an inner product. We can call we have vector spaces in more abstract setting together with the inner product satisfying some condition as is given to you. If you have such structure, if you have a subspace, then you can always define an orthogonal complement by using that inner product or dot space. So instead of the dot product here, you might have an inner product in a general form. In our example, we are focusing on the Euclidean spaces. So our vector spaces will be R to the N, and our example actually will be focusing on three-dimensional Euclidean space for simplicity. And then you can generalize that idea for any vector spaces, for any inner product associated with that vector space and a subspace. But in order to be able to understand, we will do as simple as possible. All the common elements of W and W complement is the zero vector. So this is a known fact. And another is a very important, and this is the crucial part in the definition of a direct product. This means that the intersection of the W and the W orthogonal complement of W intersect only the zero vector. There is no other intersection. So there is no dimension in the intersection because you have only one vector. If you have one point, there is no dimension. The dimension is zero. Okay, so when you apply, that's a definition of a direct sum of a vector spaces. If you apply the dimension into this summation, then we will have explicit sum. Dimension of V will be the dimension of W plus the dimension of orthogonal complement. So this is another important fact about orthogonal complements of a subspace. Next, this point means that every vector V can be written as a sum of vectors, one in W and one in orthogonal complement of the W. That's a general definition. So that's what. So these are the three important parts of related with the concept of the orthogonal complement of W. Now let's do some exercise and try to understand this abstract concept. Now we would like to find a basis of the orthogonal complement. Let's have a look this way. So you have this equation. We know that this equation in three-dimensional space represents a plane equation. Yeah. And this W is a plane. If you have a plane, then all the normals gives you the orthogonal. So that's the structure that you're having. So this is your W, and your W hat will be everything else. So if you think about your floor is your W, and the yourself as the normals and all multiples of you on upstairs and all multiples of the downstairs as well give you the complement space of that plane. So that's the structure. That's a visualization of this concept. So W is a plane in R3. The orthogonal complement is the normal. How we find the normal of a plane, as we know from the last year, will be just the coefficients of that equations that is defined by. So the normal vector is 5 minus 7 minus 1. That means orthogonal complement will be spanned by this normal vector. So that is the basis for the orthogonal complement. That is also the definition of it as anyway. And everything in the normal or multiples of normal is perpendicular to it. You have the perpendicularity, right? Everything here is a vector. Every vector here, every object here in the space is the orthogonal complement as a set to W. You might have any vector here, but the multiple of it will give you. So you're filling the space by just taking the normal and getting the all multiples of it. And so all the multiples will include the negative S1, so up and down will be included. Okay, it's now the solution of this area answers the solution of this question. But I just would like to point out a few facts about this. So the green area is extended explanation for this question. It has nothing to do, this green area is nothing to do with the solution of that, but it's an expansion of it. Of course, but you can think of that in the future for complex questions. We can think of those points for those questions, which will make us our easy. We are just understanding difficult problems in the setting of an easy setting, in the setting of easy problems. So let's have a look what I'm trying to say here. So we have, this is W, that's the plane. So this equation can be written as a matrix multiplication. So this is the 5 minus 7 minus 1, which is basically the normal vector in the row form. And you multiply x1, x2, x3 is equal to 0. This is consistent with the matrix multiplication, isn't it? So this is basically the linear system of equation to solve. You have one equation, but still you have a system of equation. So this is like ax is equal to b form. As we get used to know how to solve it. So this is the coefficient matrix, like a coefficient matrix. In this case of our coefficient matrix, it has one row, three columns. So we have one row, three columns, and the unknown matrix have three rows, one columns. If you multiply those ones, we can, because this 3 is equivalent to this 3, and as a dot product, it has enough objects to multiply with. And eventually you will find the vector one by one. So this is exactly the matrix multiplication. Everything is working in a right way. There's no contradiction here. But this definition here, this set here is called kernel of the matrix A. A matrix is this matrix, the coefficient matrix. As we know, we know that set is the definition of the kernel of A. And it is also called the null space of the matrix A. Exactly the same thing. I'm just reminding you about these facts. You were supposed to know what the kernel of a matrix means, what the null space of a matrix means, and this is the association. This is just connection. I am putting the connections together. So we can find out the basis of this, right? The kernel space. It means if you have so I'm looking at this equation. So taking the x1 alone, multiplying 1 over 5 everywhere, and keeping the x1 is alone. This is what I've done here, right? x1 is equal to 7 over 5 x2 plus 1 over 5 x3 coming from this equation. Now we have two independent variables. X2 is an independent variable. X3 is an independent variable. Three variables. Call x2 is lambda and x3 is mu. Then we will find a parametric solution. So x vector here can be written as lambda times the vector 7 over 5 lambda, and lambda is 1 here. This is why I have 1 here, and there's no lambda here, so it is 0. I'm looking at the coefficient. So x1 in terms of the mu is 1 over 5, and there is no mu in the second equation, so I have 0. And the last equation, I have mu, which is 1. So this vector x1, x2, x3 is this vector. It's a solution, as we know. So it means that the W as a set, as a space, is spanned by this vector and this vector. But since we are taking the multiples of the lambda mu, you can say that instead of the lambda, you can use 5 lambda, and then you will have the vector 7, 5, 0. Instead of the mu, you can use a 5 mu, then you will have 1, 0, 5. So this is what I've done here. So we obtain W as a subspace as spanned by two vectors, which means that the dimension of W is 2. We've just found in this, we figured out the complement of the W spanned by this vector, which is the normal. And that is that vector. And the dimension of the orthogonal complement is 1. And the addition dimension of the 2, dimension of this 1, add together, we'll find the dimension of R3. Everything is consistent. And the theorem, there exists a theorem, this is a fact, the orthogonal complement of W always is the column space of the coefficient matrix, or transpose of the coefficient matrix. In this place, the coefficient matrix 5 minus 7 minus 1. If you take the transpose of it, you will have 5 minus 7, 1. And the column space of this vector is itself anyway. So it is exactly that. Right? It is automatically, by this fact, it is an automatic thing. It is another connection. It is another perspective that we can think of the orthogonal complement of W in this case. Yep. Okay. Hopefully this will be helpful. This equations. This is what I'm saying here as well. This is what we've shown. We've just shown in this example. This is how it's work. And also we learned two things. W is the kernel of this coefficient matrix, and W, orthogonal complement of W, is the column space of a transpose. These two actually makes your calculation a lot easier. You can use directly in your calculation. Since we have the matrix, will give us an opportunity here to do more compact calculations. It will be very useful to know this little square here and this factor here will be very helpful. If you understand this, this is coming from the definition. It is straightforward. It's just just a definition. That's not a theorem. But this one is a theorem. This one is a theorem. Okay, good. Now let's have a look at another example. Again, I will explain a lot. For this question, I will explain, look, I will explain this part, this part, this part, but the actual part, in order to be able to solve this question, is this much. Okay, I will explain how this works. So this explanation is all about how to get this. But I think it is important to learn to understand how the things works. rather than having the gap all the time. I'm trying to make the logical flows each time that I am giving some information to my students, instead of saying that this is a formula and this is how you apply to it. I like to explain. I like to show you that mathematics is really magical. You start from a point and then you apply your logic, your definitions, your theorem, and it gives you a beautiful result in the end. And that's the taste of the maths. So I want you to taste it. Okay, let's do this. Okay, we have W is a subspace. It is spanned by two vectors. Now, these two vectors, so we have three components. That means this is a subspace of R3. Now, call this vector W1, call this vector W2, and clearly, and W1 and W2 are not multiples of each other. What I mean by that, there is no lambda such that you can write W1 as some multiple of W2 or vice versa, right? There is no lambda. There is no there's no real number such that W1 is equal to lambda times W2. That means that if you have two vectors and they're not multiple each other, automatically you can say that they are linearly independent. Right? That is the definition of linear independency. Since there is no lambda like that, all the coefficient has to be zero. When you make the addition is equal to zero, it's linearly independent. If you just think about it a little, you will believe in your mind as well. So since these columns are linearly independent, so that is a basis. So basically W has two vectors, linearly independent, span. Spanning set is always a subspace and has basis with two vectors. It means that the dimension of W is 2. Now, this might be tricky. Do not trust all the time that is the example that is given to you. Maybe you'll have many vectors here, and maybe some of them are span of some vectors. Maybe some of those vectors are linearly dependent. You need to take out the linearly dependent vectors out. Only the vectors, linearly independent ones, will give you the dimension, will give you the basis. Okay. These two vectors are linearly independent, so it is a basis for the space W. Okay, that's clear, I hope. Then this is the definition of orthogonal complement. This is how it's defined. For every vector in R3, because these are the subspace of R3, in general is a vector space here. Then when we dot product with every single vector in W, we must have 0. This is a very strong requirement because this is the every vector in W should satisfy this. Okay. Next. Now, for every W in W, there exists alpha beta in R such that W can be written as alpha W1 plus beta W2 because this W1 and W2 is a basis of W, as just explained. And we know that why. What is the significance of a basis? The significance of basis is this green area. This green writing here, the green fact here written here is the significance of the basis is crucially important. Every vector of a vector space can be written uniquely as a linear combination of the elements of a basis for V. Right? This was the key point of a basis. So this means since W1 and W2 is a basis, every vector can be written as a linear combination. So this is what I've done here, right? This is nothing obscure. So every W can be written as a linear combination that exists in alpha beta such that I can write. That's the definition of linear spanning set. Now I have this equation. Now I would like to multiply this equation by the dot product with an element x in the orthogonal complement. And let's see what will happen. If I have the dot product here, everything, dot product with x, then by the distribution of dot product, I have alpha and the x dot product W1 will be here, x dot product W2. So far so good. Now, this dot product, since x in the orthogonal complement and w in w, this dot product has to be 0 because this is in the orthogonal complement and this is in w. When you multiply into by the definition of the orthogonal complement, the dot product has to be 0. So this is equal to 0. Now what we have, this part is 0 and this part has to be 0. But this is 0 for all alpha beta, right? Because when we have the W runs through the all W, which means that the alpha beta runs through the every real number. So this equation holds for all alpha beta real numbers. So that is the key understanding from moving from this row to this row. The sum is 0 for all real numbers, alpha, beta, because we are thinking for all W in W. And x dot product W is always 0 as x in the orthogonal complement by definition. As I said, that condition, this condition is very strong condition. And because of this condition, this equation, this condition, we have this dot product has to be 0 and this product has to be 0. This product is 0. It means that the W1 is, that's the vector. What is the W1? 2 minus 1, 2, and W2 is 3, 1 minus 1. W1 times x. X is 2x1 minus x2 plus x3 plus 2x3 is equal to 0. That is the x dot product W1. And the x dot product W2, 3, 1 minus 1 was the W2 vector. When you multiply with the dot product with x, then you have this equation. So you have two equations. This means that these two equations needs to be satisfied for each x. This is what I'm saying. So orthogonal complement of W consists of the x such that these two equation has to be 0. So far, so good. See that exists a flow. There's no gap. One by one, step by step. Now we are here. From here to here, this is just a two linear equation, a linear system of equations with two equations, three unknowns. We know how to solve it. We know how to express it in terms of the matrices. So the coefficient matrix of these two equations is 2 minus 1, 2. And the coefficient of this equation is 3, 1 minus 1. And the x1, x2, x3 is the vector, unknown vector. And then on the right-hand side with the vector b, ax is equal to b is the general form for the linear system of equations. That is a, that is x, that is b. Now b is the 0 vector. So it is convenient. It is a homogeneous system. So this coefficient matrix, but this coefficient matrix is exactly the A transpose. We call A is the W1, the columns of A is the W1 and W2. which was the span of the space W. Now, the transpose is exactly the coefficient matrix appeared here, but this is the definition of the kernel. This is how you get there. So the orthogonal complement is equal to the kernel of the matrix A, kernel of the transpose of the matrix A. And the matrix A, the coefficients consist of the span of W. Look at this beauty. Look at this magic. Now, after this point, it is just a straightforward solution. Once we understand this one here is the key understanding to solve this equation. Once we have this, you can now, since you understand this part, you don't need to repeat it at all when you're solving equations, or if such a question appears in front of you, you just need to use this fact because we've just obtained it. You just use this fact and then solve it straightforward. So what is the solutions of this homogeneous system? So the right-hand side B is a zero vector, so I don't need to repeat it in my augmented matrix. So I omitted the 0, 0, 0 matrix in my augmented matrix. Then you apply the row operations. If you apply the row operations to this matrix, this is pretty simple. You will find in a few steps this matrix. And this matrix means that the first row tells you x1 plus 0 x2 plus 1 over 5 x3 is equal to 0, which gives you this one. 0 x1 plus 1 x2 minus 8 over 5 x3 is equal to 0 gives you x2 is equal to 8 over 5 x3. x3 is a free variable. You have one dimension of the orthogonal complement is 1, and it is spanned by minus 1 over 5, 8 over 5, 5, but you can multiply. Since this is a spanning set, you can think of the lambda like a multiplying 5. So you can, because every multiple of this will be the spanning anyway. So if you multiply this by 5, you will obtain another basis for the complement. So this is the basis for the orthogonal complement of W. I hope this is useful. I hope this makes life a lot clearer rather than only memorize things to solve. This is a quick, so if you have W, which is only have dimension 1, you have one vector spanned by for the W, then we are just, what I am doing, there are two ways of doing it. I have done, this is the one way and this is another way in two different perspectives. This way, I am using this equality. The orthogonal complement is equal to the kernel of the transpose of the matrix. So the matrix A in this time, you have 3, 4, minus 1. The transpose will be 3, 4, minus 1. The kernel of the transpose of this matrix, just everything divided by 3, will give you this row matrix. The kernel of this row matrix, basically, you have two variables because when you multiply with x1 is plus 4 over 3 x2 minus 1 over 3 x3. So x2 and x3 are the free variables. That will give you two vectors, W complement spanned by two vectors. From here to here is just a multiple of 3. And the dimension of the complement has 2, so it fits because this W is a subspace of R3. So that's the dimension of R3 is 3, and dimension of W is 1, dimension of the complement is 2, 2 plus 1 is 3. That fits. That's perfectly fine. Now for this part, you can think of this as an equation 3x1 plus 4x2 minus x3 because you think that this is the normal. And the orthogonal complement will be the plane of that normal. So you can directly write it on the plane equation with the normal 3, 4, minus 1, which will be this equation. And then this equation, if you say, for example, x3 is equal to 3x1, 4x2, x1 and x2 are the free variables, then you will obtain two vectors. The basis of the orthogonal complement you can obtain from this equation directly. That will be a solution as well. There are two different ways of looking at it. Both of them say the same thing, but a little bit of differences in them. Yeah, you're using equation this directly for the first part, and you are using the knowledge of the normal vector in the three-dimensional space for the planes for this part. I will stop for this recording now, and that's all for this part. I will continue more on the orthogonal complements. Next one will be on the projection of the orthogonal projection of a vector on the vector spaces and the complement of the vector spaces. Thank you very much for watching, and hopefully it is useful for you. Thank you.